So far, we've looked at double integrals over rectangular regions. Right? Now we'll look at double integrals over more general regions. Double integrals over more general regions. Now, by general, I mean the region might be rectangular, it might be some other shape. Right? Okay. So you are used to seeing double integrals of this form. I mean, this is what we saw in the previous chapter. Right? So the region of integration is the rectangle AB cross CD, meaning so x goes from A to B. So for example, this is AC. This corner is AC. This corner is BC. This corner is AD. And this corner is VD. So what you're used to seeing integration over this entire region. But now what we'll do is that we'll look at integration over a subset of this region. Right? And meaning we will define a function in a way that is non-zero in a particular region and zero outside of that region, and the total region is going to be rectangular. And I'll show you how we're going to do this. So let's say you wish to do this integration. Here you want to integrate over some region D, F XY dA. Right? Now D is of course some subset of R2. Now D has an arbitrary shape. D has an arbitrary shape, meaning D is not necessarily rectangular. D is not necessarily rectangular. Now what we're going to do is that we're going to try to write this integral, write this double integral we will try to write this double integral as a we'll try to write this double integral as a as an integral over a rectangular region, as a double integral over a rectangular region. Now how shall we accomplish this task? So imagine you have a function f xy, capital F xy, and this is equal to okay, so fxy is, first of all, fxy is defined on the rectangle R that contains D. How do we know that D can be contained within a rectangle R? We can do this because D is finite in extent, right? D is not infinite. So let's draw this rectangle R. So we have this rectangle R, and D is some region within R. D is some region within the rectangle R. Now this F is equal to small f, capital F equals small f of xy when the argument of the function is in D, meaning in this arbitrarily shaped region, and this is equal to 0 when when the argument of the function is in R minus D, meaning as in within R but outside D. Alright, it's within the rectangle R but outside the rectangle D. Now with this definition of F, of capital F, we can write this integration for R, region R, dA. This is equal to the double integration of the region D of small f xy dA. Why is that? Well, it's because anything outside of D, when xy is outside of D, the function capital F is equal to 0. So when we're outside of D, the integration gives us 0. So the integration over R of capital F equals the integration over D of small f. Right? I hope this makes sense to you. Okay, so now why is this useful? Why are we defining the question is, why did we define an integral, in fact a double integral over a why did we define a double integral over a rectangular region R in terms of a double integral? Why did we define a double integral over an arbitrary region D in terms of a double integral over a rectangular region R? This is the question. Region R that contains D. So that's a question. So that's a good question. Why did we do this? What motivated us? Right? So the answer is that Fubini's theorem which you learned in the last lecture is applicable only for rectangular regions. Right? So we have to find a way to define it for arbitrary regions. Right? Now let's see what this means, right? Let's see how we can extend Fubini's theorem to arbitrary regions in R2. Right? So what we'll do is we'll define a special type of region now in R2. Right? We're going to call this a type 1 region. Type 1 region. Type 1 region. Right? So a type 1 region is bounded above and below as in bounded above and below, meaning y boundaries, the limits of y limits by functions of x. Functions of x. So if D is a type 1 region, if D is a type 1 region, then D is given by x, y. Now the x limits are constant, but the y limits are given by functions of x. Right? So these are your y limits. The x limits are constant, but the y limits are given by functions of x. Now let's try to sketch some type 1 regions. Type 1 regions on the xy plane, of course, because the xy plane is R2, right? So y, x, this is A, of course this is B, and the upper curve is hx and the lower curve is gx. This is an example of a type 1 region. So, type 1 region. There's some more examples of type 1 regions. They're given in the book. This is a type 1 region. I mean, this is the one that we have sketched, between G1x and G2x. This is another type 1 region, bounded below by G1x and bounded above by G2x, bounded to the left by A, and then bounded to the right by B. And this is also a type 1 region, bounded to the left by A, bounded to the left by B, bounded below by G1x and bounded above by G2x. Okay, so let's see what happens when we try to apply Fubini's theorem on a type 1 region. So the integration of fxy of fxy over the region D, where D is of course a type 1 region, D A, this can be written as integrate over x later. First you integrate over y gx h x f of x y, right? Dy dx. So this says basically that you do the integration over y first, do the y integration first, and then you do the x integration. Do the y integration first, and then the x integration. This is basically what it says. Right, now given this definition, remember we can express integration over any region, any arbitrary region, as integration of a function capital F. Capital F meaning where capital F is given by this over a rectangle that contains D. Right. So this is equal to, as we've already seen, this can be written as capital F xy capital F xy dx. Okay, let's call it dA, right? And the integration is over R. Now how do we take R? What is R? The rectangle R. Well, we can easily define R to contain, to be this rectangle, right? To be bounded above. So this is y is equal to C, and we could extend R to be bounded below. So bounded above at y is equal to D, and bounded below at y is equal to C. So this rectangle is R. The rectangle is R, where R is given by, R is of course given by xy ax v c y t. So it's no longer a type 1 or type 1 region, right? So it's now a rectangular region. It's now a rectangular region. So let's see what we can do with this. So this can be written as this can of course be written as A B C D F X Y. CD is of course integration over y, and this is integration over x. Alright, so we can write an integration over a rectangular region in this fashion. Now, because this is an integration of a rectangular region, we are allowed to use Fubini's theorem, right? And we can change the order of integration if we so wish. So this is so this would be equal to this would of course be equal to AB. Actually, let's write it this way. If we had it if we had written it, let's write it as dx dy first, and then we'll change the order of integration. Dx dy dx dy. Since the integration is over R, x goes from a to b and y goes from c to d, and of course we should be able to write this as ab cd f xy dy dx. But the same integration should be, you can write this as the same integration. You should be able to write as AB, and then instead of CD, you could write the limits as gx and hx, because remember, f is 0 here, f is 0 here. So my limits are gx and hx. Gx and hx. Small fxy. In fact, I could write this as large fxy without any consequence. Large fxy dy dx, and this would be equal to ab gx hx small fxy dy dx. Right? So that now this same thing, right? This same expression can actually be written as, show you how this converter is. And fetch after. The same expression can actually be written as this from here we see that this can be written as AB CD fxy dy dx I'm sorry, since this is dx dy, right? So since this is actually we already have it in terms of dx dy. So this can be written as gx hx ab f of xy dy, so dx dy. Now the problem with this is that after you integrate with respect to y, you're not going to you're going to have some issues with this function, right? These functions, right? You'll have x in your answer. You're not supposed to have x's in your answer. Your answer is supposed to give you a number, right? But since the limits give you are functions of x, well, you don't you just you do the y integration first and then you do the x integration, right? So this is not something that you do, right? So what when we look at type 2 regions, I'll show you why this I'll show you why Fubini's theorem is important, right? So when we look at type 2 regions that are bounded by functions of y, they're bounded by functions of y, and the x limits are and the y limits are constant, then we'll see the actual usefulness of Fubini's theorem when applied to arbitrary regions. Okay, so let's look at some problems on type 1 regions. For example, this one, evaluate x plus twice y dA, where d is the region bounded by the parabolas y equals x square and y is equal to 1 plus x square. So first let's look at the region of integration, right? The region of integration is y is equal to is bounded. The region of integration so this is example 1. Of integration bounded by the parabolas y is equal to twice x square and y equals 1 plus x square, right? So it's below 1 plus x square, that's below 1 plus x square, and above twice x square. So first step is to sketch the region of integration. Sketch the region of integration. So bounded below by y is equal to twice x square. This is y is equal to twice x square, and bounded above by x square plus 1. Right. So x squared plus 1, yeah. Actually, it should have the parabola should have its vertex. Parabola should have its vertex at 1, right? So this is what x squared plus 1 looks like. So this is y is equal to 1 plus x squared. So the region of integration is this shaded area. Right? So there are 2 points of intersection between the two parabolas that are of course given by twice x squared. So 1 plus x squared, or x is equal to plus minus 1, y is equal to 2. Right, so this is this point is negative 1, 2. This point is positive 1, 2. In fact, they should be on the same level actually. The sketch doesn't make that obvious. Okay. Then what you do is you write the region of integration. Right. So D is a region of integration. X, y. X goes from negative 1 to positive 1. And y goes from x squared to 1 plus x squared. X squared to 1 plus x squared. Right? So D is obviously a type 1 region. Now we are to find the integration over this type 1. We are to integrate over this. We are to integrate over this type 1 region. Now what function are we going to integrate? What function are we integrating? Well, we have x plus twice y dA. So our function is x plus twice y. Over this type 1 region. So you have remember, always integrate over the functions first, right? So you do the y integration first here. X squared 1 plus x squared, and then of course your f is x plus twice y dy dx. Right, you do this integration first, right, and then you do the other integration, the dx integration. So of course you would have negative 1 to positive 1 xy, and integrate to say the xy plus y square. Integrate this over this region, 1 plus x square dx. Let's work out the integration. Plus 1, right? So xy would of course be x plus x cubed plus 1 plus 2x squared plus x to the 4th power minus x cubed minus x to the 4th power dx minus 1 plus 1 plus x to the 4th powers cancel, x cubed they cancel, so we're left with 2x squared plus x plus 1 dx, and once you integrate this you end up with 2 over 3 x cubed plus half x squared plus x, which you can integrate of course when the limits are minus 1 plus 1. So you end up with so the even part of the function, this is the even part of the function, it cancels out, and the odd part you have sorry, let's work this out. So 1 cubed plus half 1 square plus 1 minus 2 over 3 plus half minus 1, right? So so in that case you end up with uh, 4 over 3 plus 2 10 over 3. Alright, so actually we must have made a mistake somewhere here. Wait, I was supposed to find 2x squared. This is fine. xy plus y squared. Wait, did I use... Oh, sorry. Should I use 2x squared here? These are the limits of integration. 2x squared. Should be 2x squared. Let's... Sorry, this is an embarrassing mistake. Let's go over this again. So this should be negative 1 to positive 1. X times 1 plus x squared is of course x plus x cubed, right? And plus 1 plus 2x squared plus x to the 4, right? Minus twice x cubed, right? Minus 4 x to the 4th power dx. Because this step would give you 1 x cubed minus twice x cubed will be minus x cubed. Of course the x squared plus twice x squared, and you have an x here and you have a negative thrice x to the power 4 dx. Right, so obviously the odd parts of the function are going to cancel out. Only the even parts are going to contribute, right? So if you integrate this, negative 3 over 5x cubed, x to the 5, sorry. Actually, what happened to the x? Actually, right. So, and then you have minus 1 over 4 x to the 4, right? Plus 2 over 3x cubed plus half x squared plus x from plus 1 to negative 1. 2 times negative 3 over 5 plus 2 over 3 times 1 4 times 2 times 2 over 3 times 1 plus, of course, this is going to give me 2. Negative 10 by negative 6 by 5, which is negative 18 by 15, plus, so 4 over 3, 20 by 15, plus 2, which is 30 by 15, and the answer is 32 over 15. Right, now this makes sense. Yeah, 32 by 15. Okay, so let's do a problem that I leave. We can actually let's look at type 2 regions now, right? A type 2 region can actually be written as one that can be written as type 2 region is D is one that is between two functions of y, meaning the x limits are constant, xy, the x limits are constant, ax b, but the y limits, so no, I'm sorry, the y limits are constant, so you could write it as cyd. I'm sorry, for the y limit should be constant, cyd, but the x limits can be written as can be thought of as lying between two functions of y. That's a type 2 region. So let's sketch a type 2 region. So a typical type 2 region looks like. So x is between two functions of y. So this is your gy. This is x is equal to gy. This curve, and this curve is x is equal to hy, and the y limits are both, and the y limits are constant, right? So in fact any region can be expressed as both a type 1 or a type 2 region. Any region can be expressed as a type 1 or type 2 region, right? So let's look at this example 2 in the book, right? So region of integration, the region of integration is a type 1 region. That's given in the first instance. The x goes from 0 to 2 and y goes from x squared to twice x. D xy x goes from 0 to 2 and y goes from x squared to twice x. Now this is most definitely a type 1 region, right? Because y is between two functions of x, and the x limits are constant. So this is a type 1 region when expressed in this fashion. Now you could also express this as a type 2 region, but think of it this way. Let's first sketch the region, right? So x goes from 0 to 2 and y, the lower limit of y is the curve x square. The upper limit is the line twice x. Right, so this is 2 and this is 0, and we're integrating in the region between the line and the curve, right? So this is y is equal to twice x, right? So let's draw an arrow to show us that we're integrating from x squared to twice x. Let's draw this arrow. This arrow tells us that we're integrating in this in this direction, right? So the integration of any function would be in a type 1 scenario would, I mean, you would integrate the you do the y integration first, gx to hx, a to b, fxy, dy dx, right? So this is a type 2 integration. Type 2 region. This type 1 region, sorry, it's not type 2 region, type 1 region. Do y integration first. Now, for a type 2 region, of course, you do the y integration first. Now, if you have a type 1 region, you would do the x integration first. So here's how you look at it. Sorry, if you had a type 2 region, you would do the x integration first. CD hy gy hy f of x y dx dy. So you're doing the x integration first. Type 2 do x integration first. Right, now why is that? Because otherwise if you did the y integration first, you would still have y in the answer, right? So we want our answer to be numerical. Okay, so this same region here, this can actually be expressed as a type 1 region. What sort of, sorry, as a type 2 region. So this is a type 1 region. Type 1 region. This can actually be written as a type 2 region. How so? How can we do that? Let's have a look. This curve y is equal to x squared can actually be written as the curve y is equal to x squared can actually be written as x is equal to root y, and the line y is equal to twice x can be written as, this line can be written as x equals y over 2, and you can set the x limits from 0, sorry, the y limits from 0 to 4, and the integration would proceed from left to right, from this to this. So the example, so this is the type 2 region. Corresponding to this type 1 region. Now let's see if integrating over a type 2 region gives us the same answer as integrating over a type 1 region. So we have this curve to work with, this function to integrate, x squared plus y squared, right? And let's see what that what happens if we integrate it over type 1 region. It's done in the book. You should be able to do this. The answer is 216 over 35. Now the question is, what happens if we integrate x squared plus y squared? Is the function x squared plus y squared? Yeah. Let's see what happens if we integrate x squared plus y squared over type 2 region. Over a type 2 region. Okay. So you let let's see if we get the same answer over this type 2 region, right? So we integrate over this type 1 region. We got 216 over 35. Let's see if we get 216 over 35 when integrating over the type 2 region. So the first thing you do, of course, you set up the integral, but your integration over x must come before your integration over y. X squared plus y squared dx dy. This is of course equal to 0 to 4 x squared y plus 1 over 3 y cubed y over 2. I'm sorry, not 1 over 3 y cubed. This should be y squared x. Sorry, this should be y squared x. Y squared x y dy 0 to 4. So x squared y. So x square y squared by 4, y cubed by 4 plus I mean obviously plus you'd have y squared by 4 plus y squared times y by 2. That would give you y cubed by 2, or 2y squared by 2y cubed by 4 plus, so x squared y, okay, so you have a minus now, minus, so you plug in square root of y now, so you have y cubed minus y square root y, which is y to the 5 by 2 dy. It's 4y cubed by 4. Of course, the function you're now integrating is minus y cubed by 4 minus y to the 5 by 2. So let's see if we've got this right. X squared plus y squared, x squared y, I'm sorry, I've integrated the wrong function. I've integrated with respect to the wrong variable. This should actually be equal to 0 to 4 square root of y to y by 2 1/3 x cubed 1/3 x cubed plus y squared x plus y squared x, and then you plug in x is equal to y by 2, x is equal to root y dy. Now I think we're looking, yeah, this is, I think this makes more sense, right? And then you have 0 to 4 1/3 x cubed. I mean, you plug in x is equal to y over 2, you get y cubed by 8, so you have y cubed by 24 plus y square x, y cubed by 2 y cubed by 2, which is 12 y cubed over 24, minus 1/3 y to the 3 over 2 minus y to the 5 over 2, right, dy, and this is of course equal to (0 to 4) 13 y cubed by 24 minus 1/3 y to the 3 over 2, right, minus y to the 5 over 2 dy, and then let's work this out. 13 by 72 sorry, 13 by 96, not 72, 96. Six y to the 4 minus 1/3 5 by 2 y 5 by 2 minus 1 over 7 by 2 y 7 by 2 4 0. Okay, so 13 by 96 times y to the 4 is, I think, 256 by 96 times 13 minus y to the 5 by 2, 4 to the 5 by 2, 4 cubed, 64, 4 is 1024, square root of 1024. Square root of 1024. We don't expect this to be this big. Right, 15, 2, and then you have 2 by 7 times the square root of 4096, actually square root of 4 to the 7, or 2 to the 14. Right, this is how you would get the integration, right? So let's see if that 1/3 y to the 3 over 2. Should I go 1/3 y to the 3 over 2? Yeah. 1/3 y to the 3 over 2 and minus y to the 5 over 2. 5 over 2 minus y cubed by 24 minus y cubed by 2. I'm sorry, the order of integration should be reversed. So yeah, the order of integration, meaning the root what we did was we placed the root first as the lower limit, but this should be upper limit, so we have an extra minus sign here we have to take care of. An extra minus sign, so which tells you that you have a minus sign here, plus sign here, plus sign here, right. And that should actually give us 216 over 35. If you work out the calculation, if you work the whole thing out, this should give us 216 by 35. So what's important is that we got the same answer whichever route we took, whether we use a type 1 region or a type 2 region. It didn't really matter, right? We got the same answer. Okay, now let's look at another example where actually it makes sense to change from a type 1 region to a type 2 region. Alright, so this integration, right? 0 to 1, 1 to x, 0 to 1, 1 to x, sine y square, dy dx. Now as it currently stands, this is very hard to do. Sine y square dy. How are we going to do this? Well, it may be that this antiderivative does not exist. The antiderivative is sine y square. So here's what we'll do. We will first look at the region as a type 1 region and try to convert it into a type 2 region. So our type 1 region so y goes from 1 to x, right, and x goes from 0 to 1. Right, so y goes from 1 to x in fact we should sketch the curve y is equal to 1 and this is equal to y is equal to x. This is y is equal to x and this is y is equal to 1. And for y to go from 1 to x, if you look at the region, I'm sorry, not 1 to x, from x to 1. Y goes from x to 1, not 1 to x, x to 1. Having x to 1. I've been switching around the order of integration a little too much. It doesn't really matter, just got a negative sign, right? So this is the region we are considering. I think I should draw a larger version of it. So this is x to x. So this is y is equal to x and this is y is equal to 1, right? So when it goes from x to 1, this is the region, and the arrow that you draw, right, to indicate the integration, this is the arrow, right? When you go from x to 1. Now we can look at this as a type 1 region or as a type 2 region. So this is a type 1 region, but also think of this as a type 2 region. How so? X is equal to y, and of course y is equal to 1, right? We could think of it this way, right? X goes from 0 to y. Let's call this region D. X goes from 0 to y, x comma y, and y goes from x to 1, right? So now this is a type 2 region. Type 2 region. Now the question is, how does redefining it as a type 2 region help us? Let's write out the integration. remember I said Fubini's theorem helps us uh, do this. How does Fubini's theorem help us do it? Fubini's theorem helps us makes it such that we can change the order of the variables of integration. So when we're switching from a type 1 to a type 2 region, I can write the dx first, and then the dy. So the dx of course from y to 1, and dy 0 to 1. But I couldn't evaluate sine y squared in integration of sine y squared dx. Dy, but I can do sine y squared dx. This is equal to 0 to 1. X equals. Sorry, it's not x equals y to x equals 1. This is actually x equals. X has to go from 0 to y. X has to go from 0 to y, and y has to go from 0 to 1. Sorry, x has to go from 0 to y, and y has to go from 0 to 1. And of course this can return as x sine y squared. Since y is a constant when you're integrating with respect to x, y 0 dy, and this can be written as 1 0 y sine y square dy. Now y dy of course can be written as y dy, can be written as d half dy square, and the integration limits are going to be the same. So you do the integration with respect to dy square sine y square dy square. This is the integration variable, half. So this becomes cosine y square. Since this is the integration variable, so you have y square is equal to 1, y square is equal to 0. This gives me half cosine 1 minus 1. Right? So look at what we've done. We converted an integral that was impossible to do on a type 1 region, and to an integral in a type 2 region, and hence and using that we found the definite integral. Right? So converting from one type of region to another type obviously makes things easy for us. And of course you have these certain properties of double integrals that I expect you to be able to deduce. So the first property is of course the sum of the integral of sum of functions is equal to the sum of the integrals. I mean these are things you can derive from Riemann sum definitions, right? And then if you multiply a constant to an integral to a function and integrate it, that is equal to the constant times the integration of the function. And this next property, property 8, of course tells you that if you have two sets, d1 and d2, then the integration over d1 dA plus the integration over d2 dA equals the integration over dA. where D equals the union of D1 and D2. Okay, so this is actually similar to the property of single integrals, single variable integrals, so you have a to v fx dx plus b to c fx dx equals a to c fx dx. Right? Okay, and right, if you integrate a number over an area D, let's say m is a constant, and okay, let k be a constant, let k be a constant, right? And if you integrate k over D, then you get k times the area of D. Okay, KAD, where this is the area of D, and this, and you have this other property that if a function, right, of x and y has a maximum, as a global maximum and a global minimum on a domain, then we may state that this is true. M times the area of D, integrate fxy over D dA capital M times the area of D. Right, this is true if the function has a global maxima and a global minima on the domain D, on the region D. And of course, using this property, you can, example 6, you can place an upper bound and a lower bound on an integral that you that in most cases that you can't evaluate directly, analytically. Okay, so let's look at integration over polar coordinates. Okay, sometimes it's easier to do integration in terms of polar coordinates, right? So polar coordinates, the relationship between polar and Cartesian coordinates, integration over polar coordinates, right? So the relationship between a polar and Cartesian coordinates is this: x is equal to r cos theta, y is equal to r sin theta, y is equal to r sin theta, and as a consequence you have tan theta equals y by x, where x is not equal to 0, of course, and r is equal to the square root of x square plus y square, right? So this is the relationship between polar and Cartesian coordinates. Now so for example, if you have a region that's described by a circle, or a region between two arcs of a circle, well, it's best that region between two concentric arcs of a circle, it's best described by polar coordinates. I'm assuming that you're already familiar with polar coordinates from high school. Now the question is, let's say you have a region R, and you have a function of fxy dA, dx dy, or dy dx, whichever. So that of a Fubini's theorem. Now the same region R, of course, this is going to be, instead of x, you're going to have r cos theta and r sine theta. But what's going to happen to the dx dy? What is the, in other words, what is the measure of integration? What is going to happen? What is going to happen to dx dy? That's another question. Now, the way to do this is to first look at a polar rectangle, right? A polar rectangle, a rectangular region in polar coordinates, right, is one that is bounded by constant theta and constant r, something that's between r is equal to a and r equals v, and theta equals alpha and theta equals beta, right? So it's this green region R, right? And that green region R can be broken up into these smaller sub-rectangles, right? And rectangles, of course, we're using rectangles figuratively. Rectangle in the sense that each of these regions can be placed within constant values of R and constant values of theta, right? So you take the ij subrectangle, as in this one. This subrectangle is between Ri minus 1 and Ri, and between theta j minus 1 and theta j, right? This subrectangle, right? And we'll be working on this subrectangle. We'll be looking at the area of this subrectangle. Now, the so Rij, we are referring to figure 4 on page 106, page 1098. Page 1063. Figure 4, page 1063. Figure 4, page 1063. Rij is the rectangle with r theta. R goes from I minus 1 Ri, and of course theta goes from j minus 1 to theta j. Acha. Now the question is, what is the area of this subrectangle, this little green subrectangle? What is the area of this green subrectangle? Before that, we defined 2 points. We defined the center of the subrectangle. So Ri star and theta j star, these are the coordinates of the center of the subrectangle. Right? Ri star is defined by half Ri minus 1 plus Ri, and theta j star equals half theta j minus 1 plus theta j. Right, so the area of this subrectangle is, remember, this is an arc of a circle, a chunk of a circle, right? And so it's basically the area of this little subrectangle. So this is the radius Ri minus 1, Ri. So we use the sector of a circle formula. So area of the green subrectangle equals half Ri square delta theta. Delta theta is basically delta theta. Yeah, delta theta is theta j minus 1, or theta j minus theta j minus 1, right? So delta theta minus half Ri minus 1 square, Ri minus 1 square, delta theta. So this conversion is half Ri square minus Ri minus 1 square, and delta theta is of course theta j minus theta j minus 1. Well, this could be written as half, so this is Ri, not Rj, Ri plus Ri minus 1 dot on the I, Ri minus Ri minus 1, right? And theta j minus theta j minus 1. So this bit is of course equal to Ri star. This is Ri star, and this is delta R, and this is delta theta. Right, now this conversion is Ri star delta R delta theta. Right, so we can write the Riemann sum I is equal to 1 to m, j is equal to 1 to n, f of which Riemann sum are we talking about? We're talking about the Riemann sum that gives us the approximate area. Alright? So in so the approximate area of a region in polar coordinates this is equals f of Ri star cosine theta cosine theta j Ri star sine theta j times Ri star delta R delta theta. Now if I why is this the approximate area of the subrectangle? Because remember, this is basically your x and this is your y. Now the exact area, actually, and this is your delta A or d. Now the exact area and by exact area I mean the exact area of this region, or of any region in polar coordinates. Okay, of this region in I'm sorry, not the exact area, the exact volume. I'm sorry, not this is, we're not calculating area, we're calculating volume, approximate volume. Volume of what? Volume of the volume of the region below the graph of f and above the xy plane. So exact volume is of course limit as m goes to infinity and n goes to infinity of the approximate volume volume, meaning the expression that we just found out, right? And that of course is going to be equal to, by definition, that's going to be equal to now in this region, of course the region is given by let's say R goes from R1 to R2 and theta goes from theta 1 to theta 2. F of R cosine theta, R sine theta, R dr d theta. Okay, so if you want to take an integration problem that is given in Cartesian coordinates and convert it to polar coordinates, first thing you do is you set x equals r cosine theta, y equals r sine theta, and then you add this, and this is going to be your integration with respect to this is going to be your integration measure. This bit is known as the measure, right? Integration measure, and then you integrate. So for example, if we have we can have, okay, so if the integration so sometime I mean there's obviously a reason why we chose to switch to polar coordinates. If the integration area, if the area of integration is some sort of circle or arc of a circle, it makes more sense to integrate with respect to polar coordinates, right? So for example, example 2, right? Evaluate this double integral, right? In 0 to minus 1 to 1, 0 to square root of 1 minus x square. So you have minus 1 plus 1, 0 to square root of 1 minus x square plus y square dy dx. Now as it stands, okay, fine, it's possible to do this integration, but let's try to convert this area, the area of integration, into an area in polar coordinates. Right, so what is the integration area, right? So 0 to 1, x goes from minus 1 to 1 and y goes from 0 to 1 minus x square. So this looks like a semicircular region, because x goes from negative 1 to plus 1, 1 to plus 1, and y goes from 0 to square root of 1 minus x square, because y is equal to square root of 1 minus x square is the upper semicircle. It's the upper semicircle. This semicircular part, right? Okay, so this is a region in Cartesian coordinates, but the region can be expressed more simply in polar coordinates, simply by d equals r comma theta r goes from 0 to 1. Right, r goes from 0 to 1, and theta goes from 0 to pi. Right, and x squared plus r squared, so x squared plus y squared can be written as r squared. Right, so let's write this as a, let's look at this as a problem in polar coordinates. So since x squared plus y squared equals r squared, so when r squared, and you have an r dr d theta. So this is actually a rectangular region in polar coordinates. Circular region in, but a rectangular region in polar coordinates. Right. So r goes from 0 to 1, and theta goes from 0 to pi. So since there's no theta here, we could think of this as an iterated integral. So you have a separate theta integral, theta, and you separate r integral. 0 to 1, r cubed dr. We have a pi here, 1/4 r to the 4, 1 to 0, 1/4 pi. So the answer is 5/4. Right? So the answer is pi/4. So see how much more simply this could be accomplished using polar coordinates. Of course, this is of course the volume of the graph z equals x squared plus y squared, which is a cone below the graph, above the region, above the semicircular region in green. Okay, so even in polar coordinates, you could define type 1 and type 2 region. So look at definition 3. Type 1 region is when r is bounded by two functions of theta, and theta is bounded by two constant values of, with two constant numbers, right? And a type 2 region is, of course, when theta is sorry, this is a type, and this should be type 2 region, right? So we'll call it short region. Okay, it doesn't really matter what you choose to call it. You could call it a type 1 region or a type 2 region. It's entirely up to you. But what's important is converting, right? Converting between, so for example, if the theta could be bounded between two functions of r, right? But that rarely happens. So we'll probably look at the situations in where r is between two functions of theta. So for example, this okay, let's look at this problem, this last problem, example 5. Find the volume of the solid that lies under the paraboloid z equals x squared plus y squared. So we have a paraboloid. Okay, I'm sorry, it's not a cone. I mistakenly said that it was a cone, right? It's not a cone. Z equals x squared plus y squared. It's not a cone. It's a paraboloid that lies above the paraboloid, but below. And inside the cylinder, z equals x squared plus y squared equals twice x. Oh, sorry, x squared plus y squared is equal to twice x. So x squared plus y squared is equal to twice x is a cylinder with center 1, 0. 1, 0 is actually the axis of the cylinder, right? Meaning Z could take 10 is not just a point. 10Z is the axis of the cylinder. So any point of the form 10Z lies on the axis. Okay, the solid lines above the disk D whose boundary. Okay, so since you're finding the area below the paraboloid and above the x-axis, the domain of integration is this disk, right? Whose center is at 1, 0. Yeah, and it has a radius of 1, right? And of course, x equals r cosine theta, and y equals r sine theta. So we could write the disk D on the disk D. The equation of the disk can be written as r is equal to 2 cos theta, right? And r varies from 0 to 2 cos theta, and theta varies from minus pi over 2 to pi over 2. The tangent to the graph here and the tangent to the graph here. Minus pi over 2 to pi over 2. Remember, this is made up of two semicircles, so there's a different tangent here and a different tangent here. So go from minus pi over 2 to pi over 2, and you do the integration. X squared plus y squared is equal to r squared, and you have a measure r dr d theta, and r goes from 0 to 2 cosine theta, theta goes from negative pi over 2 to pi over 2. Carry through with the integration, you get the volume of 3 pi over 2. Okay, so that's the end of 15.3. Hopefully next we'll look at next we're going to look at triple integrals first of all, of course, in Cartesian coordinates, and then cylindrical and polar coordinates, and then we'll look at general coordinates. Thank you very much.